with that, I will thank you. Thank you very much, Grazia, for putting this together, and turn things over to you.
Okay. So good afternoon to everyone. First, let me thank Chris for inviting me to present my work, and then thank you all for being here. I'm going to show you my work about the tracking of changes in crustal properties. So from here, the title, from macro-scale seismic imaging to micro-scale rock physics properties. So we will discuss about, let's say, crustal parameters across scales. Just a brief, I want to show you briefly the outline of this presentation. So first, few slides of introduction to introduce the, let's say, medium properties tracking, the medium properties across scales, and the rock physics that is the core of this work, that allows to go from the macro scale, let's say from the micro scale, sorry, to the macro scale properties of rock. And then I'll show you two applications of this strategy. One's related to the Irpinia fault system, that is an active fault system where the 80 earthquake enucleated with magnitude 6.9, so, and still characterized by background seismicity. And from the other side, the Campi Flegrei inner Caldera, that you well know is still where there is a still ongoing bradyseismic crisis. And in this case, we reconstructed the structure, the 3D structure of the inner Caldera with high resolution image. And then we complement this with the rock physics experiment. So what means track medium properties? So here, few slides to show you, by considering several literature examples, the importance of monitoring medium properties, since medium properties has elastic properties, so seismic velocities, or anelastic properties like seismic attenuation, and at a different scale, so let's say laboratory and in situ experiments in controlled condition, suggest that the preparatory phase of earthquakes involves variation and changes of these properties, then can be monitored. In this case, you can see, for example, velocity of P wave, the changes of P wave velocity in laboratory experiments, or changes in P wave velocity, delta V on V, sorry, so changes of velocity and attenuation during seismic cycle, here in events of Park field. And so how much it is important to reconstruct the medium properties to monitor the seismic cycle. We see here the abrupt changes, for example, in correspondence of the Park field events. Here, another example at the laboratory scale. You can see here a schematic view of the coalescing of these micro cracks in this main fault rupture, let's say, at a small scale, of course. And here, the monitoring during a triaxial experiment of the stress and strain variation with the failure, the evolution of acoustic emission, and here the variation of velocity, of P wave velocity. And you see here an abrupt decrease of VP velocity during the main failure. So from here, these parameters allow to detect the fault evolution toward a critical state. And this is true also with other application at the, let's say, very small scale controlled experiment. This is a work of Kappa 2022. You can see here to borehole injection with very controlled condition in terms of injection volume, injection pressure, induced events, and so on. And here you can see how the permeability changes are related to fluid pressure, and how these are related then to the state of condition of the fault within the medium. So changes in medium properties can signal an approaching of a critical state. So from this, the importance to reconstruct the spatial and temporal evolution of these properties let's say in this case, around fault volume. And then the second important point that I want to raise about the, let's say, medium properties across scales. Why it is important to reconstruct the macro scale properties and composition. Here, a very simple example, a work of Vanori et al. Of 2023, in which the author, by a simple theoretical experiment, theoretical analysis, let's say, reconstruct within the medium some fibers with a different entanglement. So you can see that they simulated perfect alignment between the fiber up to a completely disordered organization of the fiber within the medium. And you can see that during an extension experiment, how much this macro scale geometry of the fiber change the strength of the medium. You can see how much, especially this disordered mode, can change the behavior at, let's say, mesoscale. So the microscale means the scale of the fiber, mesoscale means the scale of the sample. And then the disordered fibers microstructure control the bractile-ductile transition. And here, another example for a work of De Paula et al. At a mesoscale, let's say, and microscale of the field, where we can see how much these are two small-scale geometries of grains and minerals within the rocks. You can see how much at this scale is complex the arrangement of these, let's say, dolostone and anhydrites and so on. And here you can see how much these very small scale variation and complexity affect the mesoscale behavior. But not only mesoscale, a recent work of Collettini et al. In 2022 show that this mesoscale behavior is important also related to the macroscale occurrence of events. You can see from this work that the authors analyzed the off-fault events, so the events that occurred not along the fault, but in the surrounding area. And they show that the let's say the microscale properties in terms of mineral composition, you see ductile anhydrites and brittle dolostone, change the behavior of seismicity in terms of frequency magnitude characteristics, and also the location in which the events occur, along the fault or in this case of fault. So this is to show you how much is important the macroscale composition and how much this macroscale composition that can means not only type of minerals, but also arrangement or let's say how the consolidation, for example, of these minerals affect the behavior of our medium at a larger scale, and let's say at the scale of the field that is of our interest. Once we want to monitor the condition of the volume, let's say in terms of stress, in terms of pore pressure, and in terms of fluid saturating. Indeed, the third point that I want to raise is about the fluids. We know that fluids are in the subsurface, and we know that pore fluids contributes to change the medium properties and the stress state. You can see here a schematic representation of the fluid presence, let's say natural or injected fluids, that permeate and diffuse within the shallow crust. We have, for example, here the loading condition of karst aquifers that can change the condition along the fault and that can trigger seismicity, natural, let's say, seismicity. Or we have injected fluid, for example, in wastewater injection well, that can change the pore pressure around the volume of the reservoir and that can trigger seismicity or induce seismicity in this case. Or we can have in case of volcanic environments, descending meteoric water that can interact with fluids and the deep magma feeding system developing hydrothermal systems. So fluids contributes at different scales to the change of medium properties. And we know that specifically for seismicity triggering, pore fluid pressure changes triggers earthquake at different scale. We know that the fluid overpressure is one of the main primary mechanisms that cause earthquakes, since we can imagine that fluids lubricate faults and the fluid pressure, that pore pressure, reduce the effective normal stress. Then how we can at this point use the information that we have coming from passive seismicity to reconstruct the medium properties changes at different scales. So we can say surely that the passive seismicity can be used as a natural laboratory since the seismic waves that travel to the medium carries information on the rocks that they encounter and the composition and the fluid content and so on. So we will use at this point the natural seismicity as our observables to reconstruct the medium properties changes. But at the field of at the scale of the field, so let's say at the scale of the seismicity, the macro scale, the estimation of macro parameters is very challenging, also using passive seismicity. And this challenge comes from first, the limited resolution of tomographic models, and also from the very poor knowledge that we have of the small scale medium characteristics. Also in terms, for example, of mineral composition that can be achieved only with, let's say, well log and very high resolution surveys. And usually the large scale properties like the velocities or attenuation are directly used to interpret the state of the fault and the surrounding medium. So we know and we saw in literature that usually there is a direct interpretation of tomographic image in terms of, for example, fluid presence, okay, high VPVS, okay, fluids. But what fluids, what kind of fluids, what means high VPVS? Since, and we know that there can be a lot of indetermination in macro scale parameters, and the velocity are affected by several macro scale parameters, not only fluids, also porosity, changing degree of fracturation, changing in effective stress. All these macro scale, let's say, condition can affect the macro scale parameters. So directly say, okay, high VPVS means fluids is something that needs to be done with carefully, let's say. So, and this is a very interesting paper recently published on Scientific Report, in which the author reconstruct the 3D image of Mount Etna, and then by looking at the VPVS, they directly interpret the high VPVS and the low VPVS with, let's say, fluid accumulation, magmatic body, fluid fillet cracks. So this is a typical example of direct interpretation of macroscale properties in terms of microscale ones. The only means to infer something quantitative in terms of macroscale parameters is needs to involve rock physics. So what is the scientific question? The scientific question is, can we monitor the dynamic state, let's say stress state, source properties, fluid presence of macroscale volume of interest, so volume embedding fault volumes, or in hydrothermal area, or in reservoir for exploitation area? Can be this monitored by reconstructing the physical properties at the microscale, and how we can quantitatively infer something about the properties at the microscale. So rock physics is the only way to connect quantitatively the geophysical observables at the macro scales. That means velocities, impedances, attenuations, also resistivity, density, let's say. So all the parameters that characterize the medium at a macro scale, to link these, to relate these to the properties of microscale rocks. So lithology, porosity, pore fluid content, pore pressure, and so on. And here the image of the different scales at which we are discussing. So we have the macro scale involving the microns, that is the scale of the mineral grains. Then we have the mesoscale, porous rock and laboratory sample, up to centimeters to a few meters. And then we have the macro scale that can go from the well log scale of meters, of hundreds of meters, to the regional scale and the field scale in this case. That is the scale of our imaging. And I will show you then two applications of this strategy, starting from the reconstructing of macro-scale medium properties. So from one side, the Irpinia fault system, that is an active complex fault system where the 80 earthquake enucleated, characterized nowadays by a background seismicity that we use it to reconstruct the properties. We have done 3D image in terms of velocity, in terms of attenuation, and then we obtained also 4D velocity image for, let's say, more than 10 years of recordings. And from the other side, the Campi Flegrei inner Caldera, that is a volcanic system experiencing now a bradyseismic crisis with the rate of uplift that now is up to 3 centimeters for months, so very high. And we reconstructed the 3D image, and then we complement this image with the rock physics experiment. I will show you then for the Irpinia area, the rock physics modeling that we use it to downscale the macro scale properties to the micro scale rock properties. And then for the Campi Flegrei, we have done a rock physics experiment in collaboration with the Rock Physics and Geomaterial Laboratory of Stanford University for a site-relevant sample under caldera conditions. And at the end, I will show you some, let's say, results concerning the role of fluids in seismicity triggering, both for the Irpinia and the relation between the structures and the seismicity evolution within the caldera system. So first, I'm going to show you the application at Irpinia fault system. The Irpinia fault system is in southern Italy. You can see here the map. Is a northwest-southeast striking normal fault system along the axis of the Apennine chain with the high seismogenic potential. You can see here the 80 earthquake. And then we had also in 1996 another events of magnitude 6.1, then 2 events near Potenza. So we have a very high seismogenic potential area. We have nowadays background seismicity monitored by the Irpinia Seismic Network with 30 stations covering the area around the main fault of the 80 earthquake, that are these orange boxes. And we have here a cross-section showing the geology of this area, let's say the main lithological units. And we have here the Apennines, that is the storage of the karst aquifers. We have some, let's say, basins or less consolidated deposits, and then we have the basement here, and the carbonate platform, that are the ones that are interested by the seismicity. And we saw that the background seismicity with magnitude lower than 3.5 is confined within the same rupture, the same volume of the Irpinia earthquake. We have for this area a 3D velocity tomography from the work of Amoroso et al. Of 2017. And here you can see that the velocity model show very interesting feature. The author used more than 1,000 events recorded at the Irpinia seismic network and inverted this with a linearized approach with a multi-scale strategy. And you can see here the VP over VS, and two sections that are the same of the geological section here, crossing the Apennine chain. And you can see how much the velocity will reproduce the main lithological units. Here you see the low of VP in red, delineating the low of the Apulian carbonate platform, and you see here where the seismicity is, this very high VP over VS ratio within the boundary volume, the boundary fault of 80 earthquake. So this high VP-VS ratio was interpreted as fluid accumulation within this 15 kilometers wide rock volume related to the seismicity. Then in 2017, we obtained the attenuation tomography. So a 3D image of attenuation in terms of QP and QS, so attenuation factor from the area. And we found also in this case, by using microseismicity recorded at the Irpinia area, we found this image. I'll show you here the QP and the QS and two sections of QP and QS along here, the same section of the first one that I show. And you can see that QP and QS show very different characteristics. We can see that the QS has this behavior very similar to the velocity. Here you can see that there is mainly two regions, one characterized by the low QS and one characterized by the high QS that can be also looked at here, and that are very well related to the lithology, let's say, to the geological feature. And here we found around the volume where the 80 earthquake enucleated a very high anomaly in terms of QP attenuation. And then at this point, we asked, can we use the information from these macro-scale properties, especially this very anomalous QP volume where the Irpinia earthquake enucleated and where was found high VPVS, to say something quantitative about the macro-scale parameters at the Irpinia area. And so we constructed a rock physics upscaling based on the prior approach of biotheory. So we started from hypothesizing a macro-scale medium, and then we, with the effective medium theory and the Gassman relation, go to the mesoscale and construct, let's say, effective porous media, and then at which we applied the biotheory to reconstruct the macro-scale parameters. So upscaling, since we start from the characteristics at the macro scale, and with the biotheory upscaled the macro parameters, so the velocities and the quality factor. And then we used this velocity and quality factor upscaled in comparison with the one that we retrieved from the real data to say something about the microscale parameters. So, and we focused this modeling on the anomalous volume of IQP, so between 8 and 10 kilometers depth, where the QP ranges the largest value. The first step of our upscaling is the effective medium theory, since the biotheory has the assumption that the medium that we are considering is homogeneous in terms of mineral composition and in terms of fluid component. But in real cases, we want to simulate more complex media, since we know that in real cases, the medium is not homogeneous. So we want to include within our medium the complexities that can arise from different kind of mineral composition, different kind of arrangement of this mineral within my rock, and also different kind of permeating fluids within the rock. And so to do this step, we use the effective medium theory that allows to, starting from a very complex microscale medium, construct a mesoscale ones with, let's say, averaged properties. And there are a lot of modeling that can be used for this step. There are the bounds, there are the theoretical modeling, and we use it among these the effective medium theory that allows to, you see, here we have a schematization of the real rock. So this is a very tiny, this is 1 millimeters, so a very tiny section of our rock in which coexist both the mineral phase and the fluid phase. And you can see how the mineral phase can be composed of different moduli, different minerals. Each one has its own elastic moduli and its own density. Then the first step is to, you see, for example, here in this other scheme, you can have for carbonate platform, and usually seismicities within this kind of rock, you can have dolomite, you can have limestone, and you can have also clay. And then first you need to homogenize these to obtain the rock matrix, and then the rock matrix will have its own elastic moduli and also the porosity and the permeability. So how these minerals are bending together. And then also the consolidation of this grain. Then you can have different fluids within your medium. So first you need to homogenize these fluids. There are plenty of relation. The Woods equation, we use the Brie equation that allows to average gases and fluids in a better way. So depending on the type of fluids that you have, you can use different bounds in this case. And once you have your homogeneous fluids and your homogeneous medium, rock medium, you can put them together. So put the fluids within your medium with the Gassman theory. And the Gassman theory allows to go from the dry rock to the saturated rock. And this is at the end of the effective medium theory application, the homogeneous medium that contains, homogeneous means that you have one single moduli for the medium. Within this, you have all the complexity of the different part. And then we applied the BO theory, since the Gassman relation, of course, can be used also in case of elastic theory. But with elastic theory, you will reconstruct only the velocities. You need to introduce the BO theory, and you need specifically to introduce the dynamic permeability, that is a quantity that is complex, to have the attenuations. I don't want to go too deeply into the theory about this, but then it is important to introduce the BO theory, since it allows you to include not only the fluids as static, but can accounts for the flow of the fluids within your matrix. So describe also the permeable solid frame, but also the viscous fluids, and then allows to accounts for the dispersion and so the attenuation at a macro scale. And so provides, let's say, an average analysis of the mechanical and fluid behavior of the porous material. And about the strategy of our rock physics upscaling, we used some,
Grazia.
Yes.
Grazia. I'm sorry,
Yes.
can I ask you a clarification in the previous slide?
Of course.
So, assuming that you are, so if you can perform averages in a scale-dependent medium, does it require that you have a specific type of scale dependence? So you means that you have different scales, but you can extrapolate, you can pass across the scale. So is this because you are considering, for instance, you are doing the volume averages because you preserve in the volume the scale, because if the medium is completely scale dependent and the processes differ at different scales, in principle, I understood that you should not even perform an average across the scale.
Yes, of course.
Yeah,
Of course,
can you clarify this?
Yes, of course. You need to assume that the scale of variation of heterogeneities of your medium is among the macro scale. And then at the meso scale, so that is the volume that you are considering for your upscaling, this kind of heterogeneities can be averaged. So of course, the scale of heterogeneity is at a macro scale. And then at the meso scale, this can be averaged in a porous medium. So of course, it's a matter of scale. And this is because we are considering, let's say, quite big mesoscale, since these are related to the resolution that we have of tomography at the macro scale. So we are talking about kilometer scale. So at the kilometer scale, we can say, and also, let's say, 100 of meters, we can assume that the heterogeneities of our medium can be averaged, at least for the properties that we want to reconstruct.
Okay, so I understand, thanks. And therefore, do I understand well that in this case, you can properly take into account the heterogeneities of the smaller scale at the macro scale, but
Exactly.
you cannot interpret the physical processes occurring at the smallest scales because you don't have resolved them. Is this correct?
Exactly.
Okay, perfect. We
You
agree.
cannot
Thank
say
you.
something about the microscale processes. You can say only something about the properties of the
Exactly.
microscale
Yeah,
process.
thanks.
Of course, if you want to say something about the processes, you need to use more sophisticated theory, like the Pachi ones. So I don't know, the squirt flow. So you need to include in your modeling more sophisticated processes at the microscale. That includes, for example, the existence, let's say, of specific pathways from the fluid, or the existence of some patches in which you have some fluids accumulation. So yes, of course, we can say something about not the behavior of the microscale, but the properties.
Yeah, thanks.
And so another complexity of this kind of approaches I was saying before, is not only rising from the resolution of the tomographies, but also from the information that you have at the macro scale. In this case, from Irpinia, we have very few well log reaching quite superficial depth. And then it was very complex, at least to have some information about the minerals that we expect, the type of fluids that we expect. So this is another complexity for this kind of application. And we used some well for constrain the mineral phase and the superficial emission to constrain the fluid phases, since from the sensitivity test, it was clear that with the only velocities and attenuation, it was impossible to reconstruct all microparameters. So we have done several sensitivity tests to well understand what parameters needs to be fixed and what can be explored. And so we fixed the mineral phase and the type of fluids, and we explored the porosity range, the consolidation parameters, and different combination of fluids. And we found that, and at the end, we compared the observed range. So we took the volume and we took the percentile within this volume to define the observed range, and we compared the theoretical estimates with the observed ones. And we found that the velocity was very sensitive to the porosity, and we constrained the porosity up to 4 or 5%. That is very high for carbonates, and is clearly related to secondary porosity, so the fracturation in this case. We have quite high consolidation range that can be associated to hyperpressure, and then we found that brine, CO2, and CH4 was reliable at 10 kilometers depth. And so we constrained also the macroscale properties by interpreting this as an high fracturate and fluid saturated rock volumes. This is another aspect that we investigated for the Irpinia area by considering also the temporal variation of properties. And we had Stefania Tarantino a few weeks ago that presented her work about this, so I will go fast. We have here for the Irpinia area very interesting evidences of correlation between the groundwater recharge of karst aquifers in the area, the seismicity range, and the displacement. You see here how much this was correlated. Especially here is evident for the dry period. You see that we have a very low groundwater recharge, a very low rate of seismicity, and a very low value of displacement. And we, in order to investigate the variation of velocity changes during time, we have done 4D tomography. Of course, 4D tomography for passive seismic is challenging since you do not have the same distribution of seismicity of, let's say, sources during the time. So you need to properly adapt your time window in order to maintain the same resolution in time. And we developed an optimization algorithm for this. And we found at the end, I'll go fast on this, that for specifically looking at the PVS ratio in time, you see here, we have 5 windows of time during, let's say, more than 10 years. And you can see how we have some features that are the same in time, so related, for example, to geology. Here you have the law of Apulian carbonate platform, so you expect that in 10 years you will have the same geological feature, but there are also some variation, especially in the volume, that is our volume of interest of the PVS during time. So we isolated these 2 volumes, one that is the same volume that we investigated with rock physics approach, and the other here within the karst aquifers. And we found for the lower volume and for the upper volume a variation of the PVS that is quite coherent with, also in this case, the groundwater discharge and the deformation. And so we found, similarly to the work of Tarantino et al., that our medium is the variation of velocity in our medium are affected by this variation of hydrological recharge of the karst aquifers. And here, okay, the work of Tarantino. Of course, we have, for the tomographic approach, less resolution in terms of temporal resolution. So we have very wide, very large time scale window. And in this case, with the noise interferometry, the authors had the possibility to have very high resolution in temporal resolution. And you can see how much the variation of delta V on V, so velocity variation, are correlated with spring discharge and earthquake rate. So this means that monitor the parameters of the medium at a small scale, at a large scale, and also retrieve the micro-scale properties allows to monitor the seismic cycle in tectonic area. So something that is very crucial for us. Then I want to show you the work that we have done to Campi Flegrei. We obtained a very high resolution, let's say the higher resolution as possible with this huge catalog that we have now. You know that Campi Flegrei, and we are still experiencing here, you can think that our university is practically within Campi Flegrei, so it's something that is personal for us. And we are still experiencing the events, seismic events, and bradyseismic crisis. Campi Flegrei Caldera, you see, we are practically, let's say, here with our university, so are quite within the Campi Flegrei area. And the Campi Flegrei consists in 2 nested calderas that are related to 2 main eruptive events, the Ignimbrita and Tufo Giallo eruption. And you know that Caldera is located in a very densely populated area. You can see here above the Solfatara crater how much buildings we have here, practically within the Solfatara. And over the past 15 years, we know that the inner caldera portion experienced more than 3 episodes of ground uplift, you see, in 70 and the most recent 82-84. That was the first one with digital recordings, so the first one for which we have earthquakes recordings and so on. And here we are now. This is the very beginning of the uplift of the recent episode, the most recent episode, and you see here how this vertical uplift is increasing up to 30 millimeters per month in the first 2025 month. This is, yes, February. So we have also a very peculiar shape of the ground deformation that is accompanied by the seismicity. You see that we have here more or less at Rite, Rione Terra, here near the town of Pozzuoli, the highest value for the uplift, and the shape of the uplift is quite symmetrical. And we have that this uplift is accompanied by an intense seismicity, and you see that how much the number of events, the cumulative number of events, the magnitude, and the maximum depth of events is strongly related to the uplift. So increasing uplift means increase of event number and increase of magnitude and depth of the events. So it is very crucial to characterize well the shallower portion of the inner caldera, since the deep magmatic source at about 7 kilometers depth is quite well resolved from the seismic reflections during the Serapis experiment, so it's quite well constrained, while the superficial structure is very debated. Here I show you some of the paper that used both the 82-84 events and the most recent events from 2014. And then there are very debated models to characterize the shallow portion, let's say the first kilometers depth of the caldera. Of course, I say first kilometer since you can easily see from here that we have seismicity up to 4 kilometers. So this means that our resolution in terms of tomographic image will be limited to this depth. And then we apply it, in this case, the linearized tomography, but using the new code of Lomax et al. NLL SSST that accounts for also the station correction, iterative station correction. And this high quality location allow us to reduce the determination of jointly inversion of location and velocity. So we binded the locations and for obtain P and S models that we interpreted at the end by considering the rock physics experiment that we have done by using the site-relevant sample of San Vito 1 within the caldera. So here I show you the 4D distribution of seismicity. So just to give you a brief methodological idea, we started from the seismicity located in the 1D model obtained from the wells. We explored also several 1D models to have a semi-global approach for our inversion. And then we invert the events to obtain the 3D model. We locate the events in the 3D model, and we have done again the tomography. So it's an iterative inversion among location and velocities. And at the end, we used this new image to infer the structure of the inner caldera. Here, I show you the final 4D distribution of seismicity within the 3D model. You see here the Campi Flegrei inner caldera. I show with this uplift, these lines, the uplift, and you see that the ellipsoidal shape, the ellipsoidal pattern of seismicity is very clear here, and is, let's say, in the same volumes, in the same area of 82, 84 earthquake. We have that more of seismicity is here. You see here also the sections, this one that is southwest northeast, and this other section. You see that the most of seismicity occurs below the Solfatara crater, between 1 and 4 kilometers depth. We have these very well-defined alignments, horizontal alignments, and we have these deeper events offshore here along this structure bordering the caldera. And we can see also by looking at the temporal evolution of seismicity, you see here from 2014 to 2020, and then for each year, that initially the seismicity was practically mainly in this below in this volume, and then is occurring also deeper, and then also along the offshore border and deeper. These are the 3D velocity image, and you see here the two sections, so the A prime section and the B prime section here in terms of VP and in terms of VP over VS. And especially the VP over VS delineates clearly different features. And this very huge catalog that we use it with more than 10,000 events allowed us to obtain image at 200 meters scale of resolution in terms of parameterization, so very, very small scale. And you see here this feature that we call it A here in figure, that has a sort of arch shape with high VP-VS ratio. You see that this feature is interrupted here below the Solfatara, where the seismicity is with this B feature with low VP over VS ratio. Then you can see here this, let's say, quasi-ellipsoidal volume, well confined, with low VP over VS ratio that is clearly visible also in this other section, BB prime. And then there is this feature quite at the border of our image, characterized by very high VP, higher than 5 kilometers per second, so deepening toward the caldera center. And we interpret this image starting from the information coming from the wells. You see here we have San Vito 3 and San Vito 1 wells here at the border of caldera that gives us some information about the type of lithology. Of course, as we expected, mainly tuff and tuffitis with different degree of consolidation and of saturation. And to properly interpret, to quantitatively interpret our images, we have done an experiment in laboratory experiment in the laboratory of Stanford, led by Tiziana Vanorio. We have done this experiment on site-relevant rock, and we injected fluid within the vessel by changing the stress condition of the rock, and we measure the variation of porosity, bulk volume, velocity P and S, and VP over VS ratio by changing the pore fluid pressure. And we use the temperature at 270 degrees and confining pressure at 25 megapascal and 50 megapascal to see also the variation depending on effective stress. And you can see that as pore fluid pressure increase by pumping water within the vessel, we measured the velocity with active pulses in this case. Both the porosity and the bulk volume increase, and the velocities, the corresponding velocities decreases, while the VP-VS increase, and at here there is the phase transition between the vapor and the water of our fluids, and this is well characterized by a variation of VP-VS from, let's say, lower than 1.7 and higher than 1.7. And if you look again here, you can see that these are exactly the value that we observed to define and that we use it to define low VPVS and high VPVS. And so by considering together all the our results, we obtained the final interpretation of our image. And you can see here a section, a vertical section along this profile, and here is again the A1 section. You can see how this very well delineated high VPVS anomaly can be associated to the caprock. The caprock was already let's say inferred by the previous images, but here we have a very high resolution reconstruction also of the arch shape of this caprock. And this caprock, from a work of Anori et al. In 2015, is characterized as being reinforced by the fiber, natural fiber. So this arch shape is due to its high strength. So I will explain this better. Then we have this low VPVS here, anomaly below the Solfatara, that can be interpreted as highly fractured rock materials where the fluid can escape up to the Solfatara, where we have the superficial degassing. And this interpretation is supported by the very well coherence among the velocity and the velocity image in terms of VPVS ratio and the resistivity image of the work of Sinskalki et al. In 2019. And there is a very good correspondence between the low VPVS anomaly and the high resistivity plumb below the Solfatara. And then we have these very well-defined ellipsoidal volume that we interpreted as gas-dominated reservoir with low VPVS lower than 1.7. And then this is interpreted based on the results on laboratory experiment. And this gas reservoir, together with the caprock, is very well located below the main, the area with the highest deformation, superficial deformation. So the volume of gas reservoir is precisely located below the volume of the area of higher deformation. This means that these features are key in the complex bradyseismic of the Campi Flegrei. You can see here how this is sorry. This is the anomalous volume of low VPVS, and these are the isolines of the deformation. So we have that this volume is practically where the highest deformation is. And then we can say also something about the seismicity evolution, and we saw that at the beginning, the most of the seismicities was within the caprock, and then come to in the reservoir, and then occurring along the basement. So we can see that first, once our gas reservoir change its conditions, start to let's say push, in this case, the caprock and the gas reservoir in overpressure, and this caprock at the beginning start to deform up to the rupture, and then we have the seismicity here. Another important observation is that there is a delay between the uplift and the starting of seismicity. And this can be due to the high resistance of the caprock since the presence of fiber within. And so I want to show you this at the end. You can see how the volume is practically below the area of higher deformation. And then we can assume that the coupling of time-varying pressure fields within the reservoir and the coupling with the microstructure, the fibrous microstructure of the caprock, modulates the ground uplift and control its rate. Then once the seismicity starts, the fluids start to, the plates and the reservoir change its condition in terms of states and unlock the boundary faults, and then the seismicity start to occur along the boundary fault. So this high resolution rock physics image of the caldera structure allow us to say something about the dynamic, the complex dynamic of the current at rest that includes uplift, seismicity, and degassing. So the next step will be the attenuation tomography, the 4D image, of course, to look at the variation, and then the rock physics upscaling, since the attenuation is crucial for the upscaling procedure. So thank you for the attention.
Okay, that was wonderful. Grazia.
I was too long? I don't know.
No, it's perfect timing. We have perfect timing.
Okay.
I will invite people to, unmute if you'd like. Join me in thanking Grazia for really a very, very nice talk.